Welcome to the TWIML AI podcast. I'm your host, Sam Charrington. Hey, what's going on, everyone? A few weeks ago, we held our very first interactive podcast screening with Google's Kwok Le. Attendees got to watch the video interview together and chime in with their own questions, which Kwok and I addressed live during the session. We had a bunch of fun with this and got a lot of great feedback. And so while we still haven't quite figured out what to call this thing, we have scheduled our next one. And it's coming up this Thursday, May 7th at 12 noon Pacific time. This time around, I'll be hosting Lucas Bewald, founder of Weights and Biases, for a live interview screening and an interactive Q&A session. We'll be discussing data versioning, managing machine learning pipelines, managing ML experiments, and much more. You don't want to miss this one. To join us, visit youtube.com/TWIMLAI, subscribe to the channel, and then hit the bell to turn on notifications so that YouTube will let you know when we're about to get started. In the meantime, Weights and Biases is extending a special offer to TWIML listeners, including unlimited private projects and priority support. For more details, visit wnb.com/TWIML. That's WANDB.com/TWIML. That said, may the 4th be with you. Hey everyone, I am on the line with Richard Socher. Richard is the Chief Scientist and EVP at Salesforce. Richard, welcome to the TWIML AI podcast.
Aloha, great to be here. Nice to chat with you, Sam.
You said aloha, and I was surprised that you're actually in the Bay Area. I always see these wonderful photos of you all over the place, and I only get to ever see you in person at NeurIPS nowadays, and the Black and AI events and stuff like that. So it's great to get a chance to connect with you mid-year. How is everything?
Life is, pretty good. I'm very grateful. Our research can continue working on some research during this crisis now too that is specific to COVID-19. And but by and large, I sometimes joke that the PhD prepared me for several years for staying at home, eating pasta every day, and working on a computer all day. So I'm in pretty good spirits, trying to have a little bit of positive impact and still go about my work and make sure my team is doing well throughout this crisis. And it's a tough time, but I'm very grateful for the line of research. We can work remotely and do quite well.
Awesome. Glad to hear that. It is don't usually do this, but it's April 10th. That we're recording this. So what is it, week 4 for you for lockdown, shelter in place, thereabouts?
That's right. Yeah. It's crazy. The time, weirdly, it's slow and fast at the same time. Days morph into each other. The home office is just the home and the office and everything. So
yeah, time definitely does not seem linear going through this. It is very strange. But hey, before we jump into some of the main topics that we want to cover, in particular language models and some of the recent work you've been doing, applying that to the bio space, share with us a little bit about your background and how you came to work in AI.
Sure. Boy, it almost starts in high school when I really liked math and languages. And when you think about those two fields, one you would hope is true even if you go, light years in some other direction. And language is this constantly morphing system where every, teenager could just say YOLO and boom, you have a new word. And now the science of language has to deal with that. And so they marry when you try to use computers, to use math to try to understand language. So I studied linguistic computer science back 2000, in the early 2000s. And that at the time seemed kind of like an orchid, kind of cute, quixotic, niche topic to my parents. But I thought, man, if we can get computers to understand language, that would be just incredible. All the things they could do, especially if you're lazy and you want every repetitive task to be done by a computer, would be quite amazing. And so that kind of morphed into a couple of other interests and trying to use initially just statistical machine learning, eventually sort of machine learning by itself, and then AI more broadly applied to computer vision problems. But I really do think in the end, language is the most interesting manifestation of human intelligence. There's some quite incredible visual systems and apparatuses in the animal kingdom, like the mantis shrimp with all kinds of trifocal vision and so on in each eye and all of that. And a lot of animals have quite sophisticated visual systems, but it's really language that is connected to thought and culture and society and information. And so got really excited about language. And then in 2010, I saw a handful of people apply neural network techniques and extend them to computer vision. And at the time, I had also just become a little bit disillusioned myself around how much time natural language processing folks spend on feature engineering.
Mm-hmm.
And so I thought, couldn't we use some of these ideas from computer vision and neural networks for natural language processing? And it was not easy in the beginning, early days, had a lot of rejected papers, reviewers just ignoring reasonably good experimental results, saying, oh, why are you submitting neural network stuff to this conference? This is not the 90s anymore. This stuff doesn't work, and so on. But eventually, more and more people kind of joined the small core that initially was really just Joshua Benjo and Jeff Hinton's labs and Andrew Ng's lab at Stanford. And it expanded more and more, and now it's kind of the default way of doing things is to use neural networks. Of course, they've developed more and more novel architectures too, and it's just been super exciting. So now I work not just on the research side anymore, but also on a lot of applied problems. In the end, I often think about trying to have impact, and in the end, when you do research, you hope that people will pick up that research, extend it, and actually apply it to some real world problems. But if you have the opportunity to do both, do research and apply it to real problems, you kind of reduce the variance of the impact that you have. And so I work on a lot of NLP problems for chatbots and service and sales and marketing applications, trying to, for instance, automatically reply to emails or to phone conversations, or having chat conversations is a really great one. Also, we're doing a lot of stuff in computer vision, trying to identify different objects in supermarket shelves and doing complex OCR for forms, and a lot of interesting things, recommendation engines, voice, machine translation. Now the group is pretty large, and so we get to work on a lot of different things.
It's a research organization, but it's part of Salesforce, which we know as kind of a does Salesforce still think of itself as a CRM company, or is it much
No,
broader than that now?
I guess the term CRM has kind of expanded and now includes everything that you might do with a customer, right? So we're one
Uh-huh.
of the largest e-commerce platforms because customers buy stuff online.
Yeah.
We're obviously the largest sales, service, and marketing organization, but we also have helped companies integrate all their different data. Now with Tableau, we help people understand their customer data and do a lot of analytics behind it. And then we look at, where are the customers, and we help governments see their citizens as their customers and help them, especially now also in this crisis, build software really quickly, build chatbots so they can answer questions. In the end, if you go to the DMV, the Department of Motor Vehicles, and you have a question, chatbots that give you answers there are also, you're a customer there of the DMV. We work with healthcare providers where the patients are customers. So the definition of what a customer is getting broader and broader,
Sure.
and we're in all those areas.
And so with the company being in all those areas and being a very product focused company as opposed to, an academic institution, how does the company balance investments in, research with product requirements, and how does that specifically impact you and your team and what you decide to or, end up working on?
It's a great question, and it's definitely something that I think every company struggles with as they can sort of think past their next quarter and think about the next couple of years. I wear really a couple of different hats. On the pure research side, we really can work on and have a lot of freedom, and we can work on a lot of different things. And we basically look for what could have the biggest impact on both the field of AI research as well as on application fields like economics or natural language processing or medicine even, and then other areas. So there we have a lot of freedom. But then another large part of my group is really just part of engineering, and we're building real products like chatbots or case classification of emails or opportunity and lead scoring, where a salesperson might have 5,000 people they could email or call on any given day, and you can use systems to rank and say these customers are the most likely to actually want to buy your product today, and then help them kind of get through and triage that. We work with marketing where we can classify the sentiment of different tweets, for instance, or we can identify company logos on tweets and surface them, even if you don't say at or hashtag this company name. We work with industries to understand supermarket shelves and do visual things. So there's a lot of product development, and as long as that product development feels like, and we feel like we're having a lot of positive impact on the business through AI, we get to carve out a niche where we just think about all the stakeholders, not just the shareholders, but all the stakeholders of the ecosystem. And there we can work on things like even protein sequence models and medical computer vision, classifying different types of breast cancer, and a whole host of fundamental research problems and optimization of neural networks, which is pretty theoretical, as well as on some really applied NLP projects that are actually very nicely at the intersection of pure research and applied research. So, for instance, one paper we've published a while back and have extended for a while now on a sequence to SQL, where we translate natural language English questions into SQL queries. And that is a fundamental problem. You try to disambiguate language that sort of touches upon what is the meaning of a question, which is actually really hard. And one way to define the meaning of a question is, well, it's a program that once you execute it over the right set of knowledge, will give you the correct answer to the question that the person asking the question had in mind. And one way of doing that is to translate it into code or into SQL, because a lot of data in the world is stored in databases. And so that is a very fundamental question that we actually started with pure research, but now with Tableau and other, Einstein Analytics and so on, it is actually quite relevant. And business users might also want to ask questions like, how many customers bought this particular product in this particular zip code between this time range, and you just want to be able to ask that question in normal English language and get a real answer for it. And so there are some more and more connections between the fundamental research group and the applied research group, and then all the product groups and engineering groups.
That provides really interesting context for talking a little bit about one of your recent papers, which is, and you mentioned this, on protein generation.
Mm-hmm.
Even with all of that in mind, how did you end up working on protein generation?
Yeah, it's a good question. Originally, we're inspired by language modeling. So we've worked on language modeling for almost 4 years since Metamind, my startup, got acquired by Salesforce, and for a while had the best language models. There were still LSTMs or quasi-recurrent neural networks and variants of these with pointer mechanisms that could copy over words as they try to predict the next word. And it's a very interesting fundamental task in natural language processing, right? In some ways, it's NLP complete in the sense that if you can always predict correctly what the next word is, then that means you can also do all of question answering, right? I can ask, what's the capital of California? And then the next word should be the capital of California. And if you do that correctly, it means you have knowledge about the world. You can answer questions. You can ask, what is the translation of Ich liebe dich from German into English? And then you should get the translation as the next couple of words. So as you can get better and better at predicting the next word, you might be able to solve a lot of different natural language processing problems. Now, at the same time, that is kind of the long-term future. Nobody actually thinks that you could be good enough, especially not a couple of years ago, to do all of these different NLP problems as language modeling. But originally, language modeling was just used to disambiguate words. For instance, if I ask you, what's the price of wood? Is this the wood, W-O-U-L-D, auxiliary verb? or is it the WOOD, the noun from a tree would? And so, but with the price of, it's much more likely to have a noun after, and so you can disambiguate, either translation or speech recognition models, or you can come up with better selection of sentences that were generated by a translation model to say this is more fluent of an English sentence than another alternative. And so that was originally what language modeling was used for. But then we were able, with deep learning and in our group and in other groups, and now all these transformer models and BERT models and so on, really get better at predicting not just the next word, but you can also predict words in the middle of the sentence, and you train really good general representations of language that capture general knowledge. We actually use these kinds of language models to give explanations for why you choose a certain classification output. And it turns out that in several cases, they actually capture common sense even, which is really hard to capture in a logical or database kind of structure.
Can you give some examples of what you're describing there?
Yeah, sure. So the paper was done by Nazanin in our group at Salesforce Research. And basically, she created natural language explanations for common sense reasoning questions. And so the paper was, we have actually a couple, but one was explain yourself, leveraging language models for common sense reasoning. And so the idea here is we had a couple of different multiple choice questions. And if you want to give the answer, you also ideally will say why you gave that particular answer. So, for instance, if you push a glass off the table, what will happen? A, it'll float. B, it will fall down and break and things like that. And then you will basically say, oh, why will it fall down? It's not because of gravity. And so this seems like a simple thing. And for any particular small scenario, you could possibly generate all the logical consequences. But if you think about anything like,
I was going to say, it seems like a simple thing for anyone who's not involved in AI.
That's right. You go and say, oh, the person blows the leaves from a grass area using the blower. The blower, A, puts the trimming product over her face in another section. B is seen up close with different attachments. C continues to blow mulch all over the yard several times, and so on. So, these kinds of questions and knowing how to answer that, it just requires a lot of common sense, and common sense is incredibly hard to really formulate in a knowledge representation such that AI models can really make use of it. So long story short, I got a little bit off of a tangent there. Language modeling, super fascinating. Lots of other applications that people hadn't thought about that came out in the last couple of years. And in our case, we also wanted to actually make it more controllable. We had these interesting language modeling results from OpenAI that could actually generate long texts. And it was quite surprising to a lot of people that these models were so good at doing that at the time. Mm-hmm. But all you could do is you prime it with the beginning of a sentence. You say like a knife, and then it would just kind of ramble on and on. And we thought, couldn't we make this more controllable? So we added control codes based on different training data and based on basically the whole internet. So you can make a control code and say, this is a horror story. Now say a knife, and then, sort of peek through the keyhole of the door, and the door slightly started creaking and opening, and you say, oh my God, what's going on? But you can also say a knife and then say, give me a review. And so just say, oh, the knife is really great at cutting, it fits well into our kitchen, and so on. You could basically control the language modeling a little bit better, and we thought that would make it more useful. And now people can kind of collaborate with these models to generate texts, and it almost helps you if you're try to do creative writing to give you sort of spitball with you and just generate stuff, and then you can modify it. You can create marketing messages and have control codes based on these were successful marketing campaigns. And of course, you have certain things in mind, so you want to kind of play with the model and its output. So that was control.
And that paper, just for folks, we'll link to it in the show notes, but that's Conditional Transformer Language Model for Controllable Generation, CTRL.
That's exactly right. And that is the largest model. It's 1.6 billion parameter language model. You train it on a very large corpus. You can create any URL as a control token, and it will talk in the language of that URL in like CNN.com. and so on. It's quite fascinating. And for a while, we were actually worried also that it might have ethical issues, but really, I don't think that is the case. People, unlike GANs that generate images, where people thought images were, despite Photoshop, people still thought of images as a good proof for something. You can forever in human history, since we've had language, just misattribute text to somebody else. You can just write an email and say, oh, this other person sent the email. I'm like, well, you have to actually show metadata to really verify that that is really something that somebody said. So I don't think it helps with sort of creating misinformation. Also, because while it's more controllable in terms of the style now with CTRL or control, you still can't force it to say the things that are in your head. Like usually when you want to create misinformation campaigns, you have something specific in mind that you would like the models to say. But long story short.
Quick question on that. The control codes you mentioned, you can generate them from any URL. When you have something like a review or a movie or horror, I think was the example you used, does that particular code map to a specific URL that you've selected, or is there something more to that mechanism?
Great question. So the control codes are very broad. You can say like this is Wikipedia, or like a Wikipedia style, or coming from Wikipedia like training data. It can be just a URL. It could be a style, like a kid's story or a horror story. Like you can have any set of control codes, and one set of control codes are URLs. Like you can say, create me a Kickstarter campaign for like some new gadget that you come up with, and it'll literally write you a Kickstarter campaign with that URL. It's actually pretty hilarious what people have been able to generate with it in terms of the text.
And the control codes, those are you're providing those to the model at inference time. They're not baked in during the training process. Is that correct?
So they are, in that we use the whole internet as the training data. And so every URL was in some way a control code.
Sure, but you don't have to specify a subset of the internet that will serve as your control codes later while you're
You don't
training.
have to, yeah. You don't have to, but you can.
But you can.
Yeah, the control codes are very general. And some of them where we knew, for instance, where they came from, like Wikipedia, we can kind of stylize them. And we had certain groups of documents where we said, all right, these are all Wikipedia articles. So let's just say this is the style of Wikipedia. It's very factual. Mm-hmm. You don't just ramble on. You don't use colloquial language and things like that.
And so can you kind of describe the general mechanism that the model is using to base output on these control codes?
Sure. So essentially, in a language model, you have a sequence of words, and at the end, you have a classifier, and that classifier goes over the whole vocabulary. Sometimes that vocabulary can be just the characters of the English language, for instance. Sometimes the vocabulary can be full words. And in some cases, they're so-called byte pair encodings. And I don't want to get too technical, but it's basically like character sequences that are very frequent. And you can basically, at each time step, classify what's the next most likely token that you want to generate. Mm-hmm. And the control tokens are just another input in the beginning of these language models, and say, this is the current input. And then after that, you say, now start, you can also have a sequence of words to prime the model further, and then it just continues to generate. So it's essentially just another input, also in a vector representation based on these control tokens.
I'm trying to get at what's special. Like if I took GPT-2, for example, and started my prompt with Wikipedia, mm-hmm. I'm imagining that wouldn't produce the same effect as your model conditioned on Wikipedia as your token.
That's right. Yeah, because the original language models just took raw text. They didn't think about metadata of that text. So it's really hard to say like a knife and then control like in which direction you want that to go. It will mm-hmm. generate whatever is the most likely based on all of the text it's seen.
Okay.
Right. So you have no way of controlling it in any which direction you want it to go. Do you want to have a colloquial story? Do you want to have a tweet? Do you want to have a very factual story that sounds very, standard and so on? So this is kind of the metadata associated with language, and you can use that to control where the output is headed and in which general direction it should be. So then we trained these language models. It's quite exciting, and we released the whole model, and it's basically the largest model that would still fit on a general GPU that you can get on AWS, like a P100. And once it's larger, there are some larger language models that people have trained, but they become impossible for anybody else to run. Like,
Or up to like 17 billion parameters now.
that's
Microsoft.
That's right. And so, and NVIDIA had some other ones, but they're just like, okay, if you have a gigantic, $1 million cluster, then you can do this, or you want to spend a lot of money per hour of even just loading it up and so on. So we felt like this would democratize a little bit what these methods can do, and allow basically anybody who can spawn a reasonably cheap AWS instance to play around with these models and fine tune them too, and make them work for their particular use cases. And then we thought about what would other use cases be? Where else do you have data and you want to generate useful sequences? And in our group, we have Ali Madani, who's a great researcher in our group. He's worked in some medical applications around computer vision too. And he basically wanted to study the language of biology and basically try to generate proteins in a controllable fashion. And proteins, and I don't want to get too technical on the bio side, also I'm not a biologist, but basically proteins govern everything in human biology, in our bodies and viruses, everything. And so this AI system, which we called ProGen for protein generation with this controllable language model, is this really high capacity language model that was trained on the largest protein database that's available. So we had 280 million protein samples. And now we can actually do something that's really challenging for science and basically unlock the potential of protein engineering for synthetic biology, material science, and human health. And we started this project almost a year ago. And at the time, we thought about really pressing diseases like cancer and others, or material science where you can try to generate bacteria that might eat plastic and things like that. So it was pretty broad. And it's a super fascinating area of research that I think can have a lot of positive potential for the world and the environment and people. But now, of course, it's COVID-19 is on everybody's mind. And it turns out that even there, like 2 years ago, the Nobel Prize in Medicine was given to a team that was able to synthesize new proteins that didn't exist before that had a specific function. And in the case of these control tokens, now the functions can be a specific type of control token, like make the cell glow, or make this particular cell be a spike protein for a specific receptor and things like that. And that is exactly what we can now do for trying to work on viruses and antibodies and things like that, to try to generate the right antibody and things like that. So
is it just me, or is it pretty amazing that we can now build AI models that we're solving, that can be applied to what a couple of years ago won a Nobel Prize?
Yeah, well, so yes and no.
I mean, I don't want to push that too far, but
that's right. And so we have to be careful. It's still very ongoing research, and I don't want to hype it up too much until we have more real results. But basically, the previous line of research that won the Nobel Prize, they basically randomly permuted these proteins and then tested out many iterations until they found something that would have the actual biology and functions that they wanted. And in our case, we're able to reduce the search space, because there are a lot of potential protein sequences that you might get with these random permutations. But if you had a sense from reading 280 million of these proteins before, you had a sense of what's a reasonable structure, what's most likely to come after this sequence of characters and amino acids and so on, then you might create much more guided and directionally correct proteins. And we actually see, the energy, how stable they would be. And there are a couple of metrics that we show in the ProGen paper that the proteins that this model generates are much more likely to be viable to be synthesized and to have the functions that you want them to have than randomly permutated ones. And that's obviously a relatively low baseline, right? Random permutation is not that smart.
Okay.
So you can do better than random permutation. But it's really hard because the human AI, the human intelligent system has evolved over many, many years.
I.
That's right. To, deal with human language and the
Yeah.
statistics and correlations that human language has. And so we're not very good at looking at, A, B, like
Right.
D, F,
So the
E.
contribution here is not that you're making a dent in this actual problem, but rather that you're applying this language model that's built on human language to a totally different type of language that kind of underlies biology.
That's correct. And then we show that this new tool can be useful for a broad range of applications. And now we're actually collaborating with people to actually go and generate and synthesize these proteins. And we're partnering with a lot of different universities. And there's a lot of exciting space, a lot of exciting work in this space, but it's all a little bit too early to tell. We just released ProGen, and so now sort of follow-up work is in the pipeline.
And so can you go into that follow-up in a little bit more detail in the sense of to, validate the results of this model, what has to happen? It sounds like what it's ultimately producing is candidate proteins that have to then be validated experimentally. Is that the idea, or?
That's basically it. Yeah, you first want to generate them computationally, then you want to synthesize the actual proteins in real biology, create the molecules. Then you want to see if, on a very simple chemistry level, they would actually exhibit the functions that you want. If you then think you have some successful candidates, then you would want to run some animal studies. And eventually you hope to create new antibodies, new ways to deal with and protect people from certain diseases. A long line. Those are many, many steps. And obviously we don't have a wet lab and things like that. So we're going to have to partner with people on that. We only go so far.
Is there, to your knowledge, is there a role for simulation, or are we not there in terms of simulating protein structure before you go and actually synthesize?
You could, and I guess some people work in that space. It might also be helpful. It turns out it's not actually that expensive to synthesize a protein. It's about $10.
Okay.
And so
Got it.
depending on the time, cost, computation trade-offs, and so on, and if you're really reasonably certain that you're able to give good candidates to be actually synthesized, then maybe you can just synthesize them too. But yeah, it's like I said, it's very early work. Synthetic biology as a field has been around for a while, but it's still quite nascent in comparison to a lot of other fields. So I don't want to go into too many details until we have some more concrete results.
Yeah. And is the idea in this line of work around language models to, hey, we've got some interesting thing here with proteins. Let's, push that a lot further. Or, hey, we, demonstrated that we can apply this to, this biological code. What other types of codes or languages are that we can apply this to? Like, where are you headed with this general, line of research?
So I think there are a couple of really exciting areas of research, several of which have connections to language models. In some ways, I think of 3 equivalent super tasks of NLP, actually. Language modeling is one, question answering is another, and dialogue systems is the third. And they're equivalent in the sense that every NLP problem can be cast as one of those 3 tasks. You can sentiment analysis. People think of it as just classification, but really, if you ask, here's a sentence, yes, what is the sentiment of the sentence? Then the next word that you predict should be the classification and the label that sentence has. So even sentiment analysis can be seen as question answering, and then everything that's question answering is also language modeling. And in some ways, those insights were kind of irrelevant because people said like, yeah, but so what? But now we actually have these models with billions of parameters, and we may actually be able to build a single model for all of NLP. And that's been kind of my dream ever since I started in 2010 training these neural nets on language. And because I realized the underlying substrate matters less and less. It becomes more and more important, I think, in the future. to be able to train these large neural network architectures for multiple tasks. So you can have transfer learning between them. You can get to zero-shot learning tasks. Like I want to be able to have NLP systems that answer questions that they haven't seen before in the training data. And getting better at that. There are examples like that in SQuAD, the Stanford question answering data set, but it mostly extracts phrases from a document and doesn't really have to capture complex knowledge in and of itself. But language models are very tied to this. Also, for I think one of the most exciting and least solved tasks of our time, and that is summarization. We've had a bunch of summarization papers in the group too. Wojciech in our group has just released one on factual correctness and consistency of summaries. It turns out the whole field of summarization worked with pretty bad data sets, and including ourselves, some of the models that were we called them abstractive versus extractive. So the difference there is extractive summarization just takes chunks and phrases and sentences from the original document you want to summarize and just says this is an important sentence, and then you have it. Whereas abstractive, you have the hope that you would understand what's going on, and then you can rephrase it in a different or shorter form. And
some of these language models get us closer to being able to do that.
That's exactly right. But it turns out they also often learn to copy phrases from the input in just a really clever way. And so long story short, the biggest problem for NLP and summarization is, for instance, that first names, proper nouns, often have similar vector representations. So Jason, Jeremy, John, they all look like similar to these neural network models. They are a list of 500 roughly similar numbers. And the problem with that is that in a summary, it's really crucial. Like when you say like there's some murder or an accident or something, you mix up the names, it's really, really different, right? But to a model, this isn't really that different. And to all the evaluation metrics of the field of summarization, you don't get really dinged hard and reduce your metrics by mixing up one name with another. But for people, it's very crucial. And so looking at factual consistency and accuracy of summarization is something that we care about a lot and are actively working on. And there's, again, a connection to language models too.
Huge commercial implications of this. Like we're all inundated with textual data. And, if we could easily and cost effectively and accurately summarize that would be huge. I'm just speaking from personal experience and 500 open browser tabs.
That's exactly right. I think it's super impactful technology for our time, where ignorance is almost a choice for most people, right? But the fact is that there's too much information and it's hard to really get through it. And that's what AI is really good at, right? Take laborious tasks that just don't scale with people and automate them for us.
And going, full circle, or at least circling back to ProGen, I've talked to folks that are not necessarily trying to apply summarization to scientific literature, but to otherwise use AI to mine insights from scientific literature and kind of project into, where future innovation might come from. And, summarization that is, that preserves kind of the scientific essence, the facts of a, a research paper could be a step in that direction as well.
Absolutely, yeah. Like researchers, like everybody else, are inundated with too much information, right? If you try to follow the archive and see all the new papers that come around AI in just specific fields, it's almost impossible to keep up with the literature and still do your own work and not just be reading nonstop. And so I think summarization is going to become more exciting. And now that we have solved other tasks that can be a little less ambiguous, the field of NLP can kind of move towards these tougher, more ambiguous kinds of tasks. What do I mean by this? So, for instance, machine translation, you have a pretty small set of outputs that make sense given an input sentence from German that you want to translate into English. Sure, there may be like 2 or 3 different variants, like thank you can be translated as vielen Dank or Dankeschön. Like there are two options, but it doesn't make sense to just say like Katze und Hund, or just cat and dog. Like so you have a pretty small variance in the outputs that make sense for that input to be generated. On the other hand, in summarization, boy, there's so many possible variants. And when you think about it, in the end, summarization is also highly contextual and needs to, in the limit, be highly personalized. For instance, when Elmo came out, the first sort of language model that had really, really good representations, personally, to me, a good summary of that paper would have been, it's like Cove, contextual vectors, but instead of trained with machine translation, it's trained as a language modeling objective. And it works really, really well on a lot of different tasks. But if you don't know what Elmo or language models or word vectors are, that is a completely useless summary. And really, the good summary of that paper introduces you and maybe pulls in even text from elsewhere and helps you understand what is going on in the first place with this field, and then gives you sort of the incremental novelty of that new research result that comes out. So, and the same is true for every sort of conflict you might follow on Earth, or if you read COVID-19 news every day. You don't need to know, there's a virus. But if you just came from Antarctica and, for last month, and all of a sudden there's a lot of new stuff, the summaries would be very, very different. And obviously, there's different sort of reading levels if you're doing summarization for kids versus adults and so on. So I think summarization, there's a lot of interesting things that we can still do in that field.
Well, Richard, thanks so much for taking the time to catch up with me and share with all of us what you're up to there. It sounds like really cool stuff, and looking forward to checking in more frequently with you and keeping up with what you're doing there.
Yeah, love your podcast, and always enjoy talking about AI. So thanks for having me.
Take care. Thanks so much. All right, everyone, that's our show for today. For more information on today's show, visit twimlai.com/shows. As always, thanks so much for listening, and catch you next time.